Oh, sorry, I was not. Okay, I had been muted. Sorry, just one second. Yeah, so the title of my talk is Tidal Disruption and Astrophysical Phenomena. And so this is going to be somewhat exactly the opposite of what Amitav was educating us just now about. My talk will be entirely about interactions of black holes with stellar objects and how we can actually learn some things about black holes and what type of observational signatures that they can produce. Okay, so yeah, so the outline of my talk will be that I will actually focus in today's talk on tidal forces. Okay, and so I will start with what are tidal forces. These are studied from ancient times, and so we will try to see why these are still relevant today and why these are becoming even more relevant. This thing in physics today. So I will talk about what are the theory and what are the observables of in these tidal interactions, and I'll talk about some basic formalisms, and then I will talk about how to incorporate Kerr black hole solutions which are yet to be understood completely, and then I will summarize. So these are based on these works by our group, and for a very nice review of tidal interactions, I can point out to the Space Science Review 2021 by Jonker et al., where there are several articles which deal with almost all aspects of tidal disruptions. And this work is based on things done with Pritam, Shashwato, Devajyoti, Aryavrat, and Adarsh. And so let us begin. So this is the very famous, what is called as the Hertzsprung-Russell diagram in in stellar evolution. So these are called the main sequence stars, and the sun is somewhere over here. And these stars will evolve. Some of them will evolve into red giants. Some of them will evolve into supergiants because of their internal chemical properties and chemical reactions and things like that. So sometimes, there'll be hydrogen will be exhausted inside. Then some helium burning will start, and then there's a very delicate balance going on between the gravity and the pressure due to these nuclear interactions. And so sometimes the core will collapse, some things will expand, some very beautiful things happen. And so therefore, due to internal mechanisms, starts on the main sequence. Okay, so they will basically climb up the HR diagram, that is go as in towards your top left. And then ultimately there will be a red giant phase, and then it will shift towards the left, and then finally one possible scenario that a star will settle down is in a white dwarf scenario, or of course we know that there is this very famous Chandrasekhar limit. So it can be a white dwarf, it can be a neutron star, or if the star is sufficiently massive, it can turn into a black hole, and so all these types of things are possible. So this is basically some of the known reactions, some of the known processes by which the star will reach its end. So one process is like over here, if you can see my cursor, so there's a sun-like star which will form a red giant, and then there will be a planetary nebula, and then the type 2 supernova explosion finally will result in a white dwarf. There are other situations also. I mean, there are many things are given in this figure, but some of them might actually take a long time, like more than the age of the universe, which have not been observed till now. But roughly speaking, the ultimate ends, if you can look at the right-hand side of the of these arrows, they're either black holes or neutron stars or white dwarfs. Okay, and these are very natural outcomes. So these are outcomes when you leave a star alone, and purely by internal mechanisms. If these things, the internal mechanisms will trigger off various types of reactions, and if you wait for a long enough time, then by evolution, so there is the hydrostatic pressure balancing the nuclear, the pressure, and so all sorts of things will happen. And finally, if you leave a star alone, then the star will settle down to one of these, the star will die, basically. It will be either a white dwarf or a neutron star or a black hole, and whatever. Now, what happens is that there might be a more dramatic situation when a star meets a likely predator. Predator as in a black hole or a very massive object like maybe a neutron star. So if you have a sufficiently ferocious predator like a black hole, you can actually eat it up as a whole, or it can rip it apart, causing an unnatural death of the star. And this happens because of what is called as non-local gravity. And non-local gravity will be the focus of my talk today. And this non-local gravity is something which are normally called as tidal forces. And they give rise to very dramatic astrophysical phenomena. So the reason this is important is that, I mean, as far as I know, in the next few years, there are missions which are going to provide images of these tidal disruption effects. And the hope is that one would actually be able to comment on the nature of black holes as well as the nature of stars from an experimental, from an observational point of view. That is, how gravity really works is something which we do not fully understand near the event horizon of a black hole, for example. Okay, so some such questions are probably going to be answered in the near future when we look at these things. Okay, so now let me first talk about the importance of tidal effects. Okay, so tidal effects, as I told you, are one of the most dramatic features of non-local gravity, and it can tear apart a massive object when non-local forces will exceed the self-gravity of that object. And the important thing is that these can actually produce observable luminous flares. And these tidal effects, as you all must be knowing, this is one of the main physical processes in accretion disk formation. And accretion disks are also, they have been very well studied, and still studies are going on. I won't say they are fully understood. But some of you may have heard that, in not so long back, in July 1992, there is this comet Shoemaker-Levy 9, which broke into 21 pieces due to the tidal forces of Jupiter and collided with Jupiter in July 1994, causing huge impacts on the surface of that planet. In fact, it is said that the energy of collision of one such thing is probably about 100 times the total nuclear arsenal that we have in the world today. So such was the impact of these tidal interactions, and you can see some very nice images when this is getting ripped apart. You get a very fascinating view of the interior of that film. Okay, so this was about a comet, but now when the star gets ripped apart due to tidal forces, okay, so you can get a very fascinating view of the interior of the star, which is crucial in understanding many things like stellar composition, stellar evolution, and crucial things are the things which I will talk about are fallback rate of debris and things like that. And also, it can provide you with very concrete information about the object by which it has been tidally disrupted. Okay, and those will mostly be black holes for today's talk. And another good reason to study these is that these can also provide astrophysical tests of gravity beyond general relativity, because so there are many theories, FR gravity and maybe beyond Hondesky theories of gravity. So all these gravitational theories, they will have some kind of a low energy limit. The low energy limit of these theories will be something like what you see as the Tolman-Oppenheimer-Volkov equation in the Newtonian limit. Like they will tell you about the pressure balance equation, the hydrostatic equilibrium condition inside a stellar object. And what happens is that when you go to theories beyond GR, so these sometimes, I mean, technically it's called when the Weinstein mechanism is partially broken. Some of these theories may have distinct imprints in the hydrostatic pressure balance condition inside stars. And if you could study the theoretical aspects of tidal disruptions, because tidal disruptions are mainly to do with these hydrostatic equilibrium conditions, then by looking at the observational data, you could actually manage to give bounds on those parameters, and in fact, a large amount of literature, present-day literature exists which attempts to constrain this theory so that you're not just saying anything that you like. I mean, so you could actually give bounds on your theory by these observations. Now, what happens is that in this, what we quickly realize is that in these situations, analytical computations are impossible. So I have given you a picture on the right-hand side that, you see that if you look at the green the green line coming from the right-hand side, so there is a black hole which is sitting, a Schwarzschild black hole which is sitting at the position 0, 0. And so you could see this is 0x and 0y. And there is something which is coming from the right, and then it gets tidally disrupted. So this is in a parabolic orbit. And when it gets tidally disrupted, and some part remains, which you call as the core, and some part is getting accreted by this black hole, which you see as this circular thing. And therefore, you can imagine that no amount of analytics is really going to help you over here, because this is a real-time dynamical process where things are getting disrupted. So therefore, I mean, and this is, by the way, this is one of the very simplest type of phenomenon that I have depicted. And there can be more complicated things where there is a binary which is both of which are rotating around each other and stuff like that. But in any case, so therefore this calls for a numerical treatment of the whole phenomenon. And so therefore, I mean, what I would be interested in talking about today is stars which are actually in specific orbits, okay, near a black hole. So this orbit can be circular, this orbit can be elliptical. But what I want to emphasize over here is that you notice that when I have an elliptical orbit, or even if you make the eccentricity to be 1 and you have a parabolic orbit, okay, so there is a point where the star comes closest to the black hole, okay. And at this closest point, the interaction with the black hole would maximize in that sense. So if you consider a star to be, for example, if you consider a star to be, a fluid body, and so if you consider, let's say, which has some thermodynamic equation of state, so what will happen is that this tidal forces will try to stretch the star. Now, once it is stretched, it naturally tries to gain equilibrium by contracting, okay, because the self-gravity will then come into effect. And therefore, it will start some kind of oscillations. Okay, so this is one of the very basic and which has been studied for a very long time. So these oscillations, so when the star will start oscillating, okay, and because the fluid particles are stretched, and then because of self-gravity, they try to contract. And of course, there will be some heat dissipated because there is some viscosity inside. And so there would be a change in luminosity of the star. That is how much energy it is emitting, because some part of the orbital energy will go into the oscillation energy, and all sorts of things will happen. And in fact, these are very well observed things. So these, as I said, tides can cause disruptions, but what I just told you means that it can cause love also. So these are called heartbeat stars, or stars in love, where two stars are basically rotating around each other, and because of the tidal interactions, they produce these stretchings and compressions, and because of that, there are some observed patterns in the luminosity which are very similar to what you see in the ECG of a human heart. So these are also, that is why these are also called heartbeat stars or stars in love. And as I will tell you in a little while, I mean, there are very important things called tidal torques. Basically, because that a tide will make a star get deformed. So the deformation will actually be asymmetric in general. And because the star is actually coming in some kind of orbit, okay, so because the mass is now being unevenly spread, it will actually cause a torque which might make the star spin up, or in more common in planetary situations, in suppose the Earth-Moon system, you know that the moon is actually only one side is facing the Earth. So this is the dark side of the moon. And this means that, when the moon has one full revolution, it also undergoes one full rotation. So you see only one side. That is also due to the tidal locking of the Earth and the moon. And the moon will also have tidal effect on the Earth. So the Earth's actually spin is slowing down, but it's a very minuscule amount. So we need not worry about that very much. But so these are some of the very, very important aspects which one actually observes and which one actually, we hope to understand the full physics of it. And let me tell you that, about tidal, this thing, I mean, one really does not know the strong gravity effects of tides, and that is what is going to be the focus when this this observational data come in. This is really going to be one of the focus in research on GR. Okay, so let's start with some little bit of mathematics. So, so a very familiar example which you study in first year courses are, if you consider the Earth over here and if you consider the moon. So basically the effective force lines I've drawn over here. And so this is the x-axis, this is the y-axis, and r is the radius of the Earth. And if you compute, if you do if you take the limit that small r is actually much greater than capital R, then you get the familiar expression for the tidal acceleration, which at point A is actually towards the moon, which is over, it's like goes like 1 over r cubed, okay, like a dipole term. And the dimensionality is fixed by, because the Earth's radius appears on the numerator. And at point B, it is basically like, going towards the left. So in general, there is a stretching. And as I told you, that this deformation, this stretching, this is what I was telling you. So when a star is stretched, so this is some figure I've taken, in some work on Kerr black hole of equatorial orbit. Don't worry so much about the exact, the field lines and all. The point is that you can see that a star, when it is stretched, and it is actually going around a black hole like this, and it is in a stretched position, it is not hard to believe that, because of the stretching on these sides, okay, so there are these torques which will maximize at periapsis. Periapsis means, if you can see this, black dark spot over here, this is the black hole. Periapsis is the closest distance from the black hole. Okay, and these will actually give rise to very, very beautiful physical phenomena, as I am going to tell you. Now, how do I theoretically, how do I analyze such a situation? Well, the first take is something that people have been doing for, since the 1960s. You go to what is called as a Fermi normal coordinate system. So you basically need, because, a star is following, let's say, to a very good approximation, it's following a geodesic, at least its center of mass is going along a geodesic, and what do you say, the extent of the star is, we'll say that the star is actually very small compared to the scales at which you are talking about, compared to the the distance of the star from the black hole. So if you imagine that the center of mass of the star is following a geodesic trajectory, then you could always go to you could always set up a local tetrad basis which moves along with the star along the time-like geodesic, so that the space-time is flat all along the geodesic. This is the very famous construction by Manasseh and Misner in, I think, 1963 or 64, which have been used a lot in studying these in studying these tidal disruptions. And so the basic idea is that you set up these mu primed are your global coordinates, and the mu are the local ones. So you could actually set up these tetrads so that the metric is locally flat everywhere. And in terms of these mu alpha beta coordinates, the Christoffel connections are 0. The Riemann tensor remains non-zero. This is valid throughout the geodesics. And importantly, the basis vectors, according to the construction of Manasseh and Misner, they are parallel transported along the geodesics. Okay. So the strategy for understanding tidal effects would be the following. For a generic stationary space-time, you construct Fermi normal coordinates. These are well known. For Kerr black holes, I mean, the expressions are lengthy, but these can definitely be calculated. Then what you do is you equatorial, parabolic. I mean, you can go to the off-equatorial plane, but the things become much more complicated over there. So you choose the energy and the angular momentum appropriately. Then, because you are in the locally rest frame, you could actually solve the hydrodynamic equation of the fluid star in the Newtonian limit, right? Because you have gone to this Fermi normal coordinate, so you are in the locally flat frame. When you are in the locally flat frame, you could, of course, you have to take orders of, in approximation, but you could solve the hydrodynamic equations in the Newtonian, in the Newtonian spirit, and then you could actually there are very famous papers, one by Ishii, Shibata, and Mino, where they show how you could obtain the critical density below which the star is disrupted, and it gives you parameters, at which the tidal disruption will take place, blah blah blah, and so that's all fine. But this is okay. But we have to remember that this whole thing is like it's like a static type of analysis, because what you would really like to do is to obtain some results which you, as an asymptotic observer, will observe in real time. Okay, so you really cannot go to the locally flat frame of the star and then do your calculations over there. So this is a very beautiful thing which people have been doing for 2 or 3 decades now. But then we have to move. I mean, if you want to test it with real observations, you have to incorporate dynamics. Okay. So now, when you incorporate dynamics, so what you would do is actually, you would understand this tidal disruption events if you can follow an object in real, that is Newtonian time, as in the coordinate time as seen by an observer at infinity. And you have to formulate the whole thing in terms of the global coordinates actually, and not going to a special reference frame in which like the Fermi normal coordinate system. And now the problem gets complicated. Complicated in the sense that, remember, as I said, that in the Fermi normal system of the last year, you actually have the observer on the star who is seeing a flat Minkowski metric and deals with the hydrodynamic equation in the Newtonian limit in the presence of some potential, some tidal potential. Now that simplicity is lost over here. So here, what you will have is, so there is a fluid system, which is the fluid star, which will have its own self-gravity or whatever. There is a black hole, which is producing some metric at the location of the star. And of course, you cannot just add up these two things. So you would, of course, one way to do it is to just solve Einstein's equation P mu nu equal to G mu nu. But as I said that, these things have to be done numerically and need high performance computing. And typically the full numerical GR, as far as I know, is numerically expensive. And one resorts to some approximations in which you say that, okay, I will be a little distance away from the black hole, so that I could still, in some sense, incorporate Newtonian hydrodynamics and along with geodesic equations for the individual particles. So some such things have to be incorporated. But this problem is, of course, at the heart of everything, that you have a gravitational field produced by a black hole. You have the gravitational field produced by the fluid in the star. How do you manage the two together if you are not really solving Einstein's equations? But anyway, so what I will do is to tell you about these approximate methods in which we really don't worry about this. And of course, these are not I'm not imagining this. You could actually calculate the local scale of curvature of gravity. And if this local scale of curvature of gravity is much larger than the radius of the star, then you are sort of in the safe regime. And so that's how we'll do. So this is a picture that I have shown you, where there is a star which is getting tidally disrupted, and this tidal disruption is now happening. Don't worry about this lambda and these things. So these are related to some rotation parameters I'll come to later. But this is how basically it looks like. Okay, And as I showed you in one of the previous slides, I mean, the process is actually enormously complicated because there would be, these are called the tidal tails, So one part of the tidal tail will actually circularize and fall into the black hole. You could calculate the specific energy of the two tails, and one part will have negative energy. So it will be bound to the black hole, it will fall into the black hole. The other will actually escape. So once the tidal disruption happens, okay, so then it doesn't anymore look like any spherical object to in any imagination, and the whole thing will be quite complicated. So at this point, let me just show you a couple of videos. I hope if you can see my screen. So this is an effect of sorry. This is an effect of circularization. Can you see my screen, Srijit? Is the screen visible?
Yeah, it's visible.
So this is, you see, this is the black hole at the center, and the debris from a full tidal disruption is trying to circularize, and this is how the accretion disks form. This is actually a numerical simulation. Okay, so finally, many things will happen. There will be energy exchange. There will be this, that, all sorts of things will happen. But finally, this is the type of thing that will happen after a full tidal disruption. In the second one, I'm showing you. See, there is a star which is approaching a black hole. So the shape of the star is shown by this red, yellow, bright color. And look at the star. It is coming from the left. It is coming towards the periapsis. The star is deforming, and it is also turning. It is rotating. And after a long time, so now you can see the black hole is on the top. This is what it looks like, and it has formed a symmetric tail, in the two directions. And then that is how this process goes. Okay, so coming back, yeah. So coming back, now there are several parameters. So this is basically the essential thing that we will want to study. Now there are several parameters that you will need to specify. So during the tidal disruption effect, so one is black hole mass, black hole spin, star can have a mass, the stellar radius, the stellar spin, the equation of state, the stellar orbit, the eccentricity, and the periastron position. Okay. And now, from this list, black hole mass and black hole spins can be estimated these days with reasonable accuracy. So typically, there are three types of, you categorize black holes into three categories. Stellar mass black holes, which are like, less than like about 100 solar mass. Intermediate mass black holes, which are about 10 to the power 2 to 10 to the power 5 solar mass. The supermassive black holes, which are like 10 to the power 5 solar mass, say greater. And it so happens that observationally, these stellar mass black holes, there are a lot of evidence for stellar mass black holes and supermassive black holes, but very few intermediate mass black holes have till now been discovered. Okay, and this is the reason why these intermediate mass black holes are also sometimes called as a missing link. Because, how does a supermassive black hole forms? Probably it forms like a stellar mass black holes, and then, it keeps accreting more material, and there are black hole collisions, this, that. So at the end of the day, it will form a hugely massive black hole, but it has to go through the intermediate mass phase also. But it turns out that such intermediate mass black holes, there are only 4 or 5 observations as far as I know. Okay, so it's not very well established. So it is very interesting to understand what will be tidal effects, near intermediate mass black holes, which can serve as a smoking gun signature of these black holes, because you don't see them very often. Okay, now so you have all these, many parameters. But to complicate this process further comes the following things. First of all, there is no spherical symmetry. So people have tried, slowly rotating, stars where you could actually, where you actually expand some things in spherical harmonics. But the pictures that I showed you, if you remember, I mean, they're deformed so much that those really do not work. Okay, I mean, you can have some analytic estimates, but it's in principle, it is not very accurate. Secondly, when you have a star in an off-equatorial orbit, okay, there are additional complications because, for example, for Kerr black holes, then you have a non-zero Carter's constant, and you have to deal with that as well. Okay, so there is another conserved quantity. Now, the spin of the black hole may not be aligned with the spin of the star. That's another thing. So now it so happens that if these are not aligned, then there are processes by which the spins will tend to align with each other, but those are later. The equation of state has degeneracy. How do you know the exact equation of state? Well, one possibility over here would be that you consider white dwarfs for which the Chandrasekhar equation is a well-known is an accurate thing. Achha. The second, the another thing is that stellar orbits might not be possible to track. I mean, you don't know. You are not going to focus your telescope and on a star and you say, okay, this is coming and this will be disrupted and I will observe that one. That doesn't happen. So you actually you come to know about the tidal disruption when there is a luminous flare. Okay, so you are not really tracking a star because you don't know. I mean, it's not viable to keep tracking a star thinking that, okay, so this star will be disrupted. Nothing like that. Okay. The other problem is that, say, for example, large stellar spins, okay, they may be typically associated with large magnetic fields. And therefore, you have to actually simulate magnetohydrodynamic equations. And then these disruptions may be full, they may be partial, they may be in elliptic orbits, they may be in parabolic orbits. How do you fix all these things? So it's a big landscape. And as of now, as far as I'm aware, there is no real answer to how to accurately do these things. But these attempts are going on. Now, so when I showed you the previous this thing, so for example, I showed you this, So there is basically, this is the debris which is falling back into the black hole. And there are some estimates of the minimum time that a star, that the debris will reach to form a black hole. So this is that estimate. And from here, you can calculate the peak fallback rate of the the debris. Now, this is actually an observable. This is observable because when the debris is falling in, it dissipates energy, and when it dissipates energy, you could actually locate that in a telescope, and you could actually look at the process of dissipation of energy. And it is a very well-known formula that this m dot has a scaling like t to the power minus 5/3, but t is the coordinate time. Okay, and of course I have I have taken the rough analytical estimate, but it turns out that when you have this full tidal disruptions, it actually follows this minus 5/3 law very closely. So how do you characterize tidal disruptions? Well, you first say that you define something called a tidal radius, which is basically like the star radius into the black hole radius divided by the black hole mass to the power 1. How does this come? This comes simply by equating the tidal acceleration that I showed you with the gm by r squared. Okay, so you do that, you get to these are very rough estimates, and people usually take them because there are no no better ways of characterizing things. And there is something called the impact factor, which is the tidal radius divided by the radius of the periastron position. That is the closest distance of approach. So typically, the tidal radius is always greater. It should be basically, the tidal radius should be greater than the periastron if if the star has to be disrupted fully. If the tidal radius, that is roughly the place where the star will be tidally disrupted, is less than the periastron position, then the star might not be disrupted, or it might actually be partially disrupted. And very interestingly, if you calculate these quantities for white dwarf, see, because white dwarf, what happens is that the mass radius relation is known. Okay. Once you give me the mass of the white dwarf, I will give you its radius. So if you calculate the tidal radius of white dwarfs, you will find that if you have a supermassive black hole, that is a black hole which is like 10 to the power 5 or 10 to the power 6 solar mass, the tidal radius becomes less than the Schwarzschild radius of that black hole, which means that a white dwarf will never be tidally disrupted by a supermassive black hole. It will just be swallowed alive. Okay. So there are some of these types of things which actually put some constraint. Like, for example, if you are considering white dwarfs, you do not consider black holes of all mass. You consider only black holes of intermediate mass or stellar mass and things like that, but they are very few. So typically, so these are the observables, these are the, these are the parameters, these are the observables, and these are the problems. Now, where does one go from here? Okay. So let's see how, I'll just probably be very brief about this slide. By the way, is there any question in between, Srijit? Is there anything?
Yeah, there is one question.
Yeah, please.
It is by Sanket. He is asking, tetrad frame should lie on the orbit of star evolving around the massive object. Then along with it, how star will tidally disrupted in the size of local tetrad frame?
So here actually the thing is that you never study the tidal disruption of the star in real time. Actually, you actually study the deformation of the star in the local frame, and then you know what are the density, what is the density of the star, and you can find out the critical density beyond which the star will you say that the star will be tidally disrupted. But yes, there is really no real time dynamics in the Fermi orbital. Okay.
Sanket, are you satisfied, or else you can just unmute and get it clarified?
Yes, sir, I am satisfied with.
Okay.
Oh.
Okay, so in the Schwarzschild case, so these are some mathematical formulas that we'd use. We write down the metric over here. There are two killing vectors, and you can calculate the the conserved energy per unit mass and the angular momentum per unit mass. You normalize and you find out what is dr d tau. Tau is the proper time. You find this out. And now, because you know dt d tau, then from this dr d tau, you can calculate r dot and you calculate phi dot by using dr dt is equal to dr d tau divided by dt d tau. And you can also, given an orbit where E is the eccentricity of the orbit and P is the semi-lattice rectum, you can calculate the energy and the angular momentum like this. And then at the end of the day, because there is no spherical symmetry, you always have to work in Cartesian-like coordinates. And these Cartesian-like coordinates makes things even more complicated. But in any case, for the Schwarzschild and for the curve, you can work out things in these Cartesian-like coordinates. And I finally written down the expressions over here, where this xi double dot is like x, y, and z. And of course, this r appears and the r dot appears. So you have to again replace them back with x, y, z. And then you add in. So there comes the approximation. So you assume that you keep the star sufficiently far so that you are in a regime where you can still apply Newtonian hydrodynamics. So you write down the Euler's equation over here, couple the whole thing, start from some initial configuration, evolve it in time, and see what you get. Okay. So this is basically done using something called smooth particle hydrodynamics. Okay. At least we do it in that way. There are other methods of doing it, like grid-based computations, which are more numerically expensive. So what we do is basically, just to be very brief about this, we take an infinitesimal fluid element and approximate it by a particle. This is a Lagrangian method. There are no grids, no boundaries. Conservation of energy momentum are automatic. Hydrodynamic properties are evaluated from neighbors. So there is some binary tree, and far field gravity is calculated using multiple moments of particle groups. Temporal evolution is done using time reversal, and there is something called a symplectic leapfrog integrator. Individual time stepping ensures that each particle evolves in its own time scale, and etc. And so this is what we use. We use a homegrown numerical smooth particle hydrodynamics code, which is written in C. Actually, it took about a couple of years to develop this code fully. And for the data analysis, we use Python Mathematica Splash, and it's parallelized using an OpenMP and MPI. We work with 0.5 million particles, with convergent tests being done using 1 million particles. And the simulations are carried out in the Param Sanganak facility as part of the National Supercomputing Mission. So if you just to give you a little bit of history, the first SPH code was written in 1982 by Nolthenius and Katz. They used 40 particles, to study the tidal disruption of a one solar mass star by this thing. A significant improvement was in 1983, which used 500 particles. But now we are in a position where we can use, up to 1 million particles. Okay. So this is one result that I wanted to show you. I mean, how this is basically the tidal disruption of of a solar mass star with 100 solar mass black hole, and so the star starts off its life like this, gets deformed, and this is basically in a parabolic trajectory. Okay, so that is what happens, and after a long time, if you track the the motion of the remaining core and the center of mass of the star, what would have happened if it had not tidally disrupted? They start differing significantly, and this is what we found. This is an equivalent simulation for one solar mass star with 1,000 solar mass black hole, and this is actually for a white dwarf, a one solar mass white dwarf with 1,000 solar mass black hole. And so here we have, what we have done is we have taken the star to be in a parabolic trajectory, and we have shown one particular interaction of the star with the black hole. So these are some typical things which come up. And as I said, that the observable is actually the fallback rate. So here you can see that I have plotted the fallback rate of debris, these are all numerical computations. So I've plotted the fallback rate of debris for a one solar mass white dwarf with the skew is 10 to the power 3, means the mass ratio is 10 to the power 3. So this is a 1,000 solar mass black hole. And you can see that these observables, these fallback rates, what we find is that when the star is in elliptical orbit about the white dwarf, they do not asymptote to that minus 5/3 behavior. And in fact, what we have shown over here is that I've plotted over here the asymptotic value of the power law scaling. This asymptotic value can go from this minus 1.5 to minus 2.5, which implies that, very roughly speaking, if you see that your the asymptotic behavior about the fallback rate, which is an observable, is not minus 5/3, then probably it is being disrupted by intermediate mass black hole. So what we propose is that this might actually be one particular smoking gun signature for a intermediate mass black hole. Okay. Now, so recently, so I will probably spend the last 10-15 minutes with some more recent developments. So recently it is being found that stars can actually have very large spins, because if you talk about white dwarfs, observations show that most white dwarfs are slowly spinning objects with spin period for several hours, maybe days also. But in 2020, some people discovered a white dwarf in what is called as a cataclysmic variable. Okay, cataclysmic variable means that it's a binary system which are accreting from each other in bursts. Okay, they're not continuously accreting. Anyway, so these are white dwarfs in cataclysmic variable system, which is spinning with like 29.6 seconds. 30 seconds it's going around its own axis. And in 2022, a similar white dwarf in another system was found with 24.9 seconds, but these are in binary systems. Okay. And in 2021, that is 3 years back, astronomers discovered an isolated white dwarf, and isolated as in, it's really not a binary or anything, which is spinning with a spin period of a little more than 1 minute. And then theoretically, there are a lot of works about it. You consider the metric due to the white dwarf, and you could actually show that in principle, they can have a very small spin period, maybe of the order of a few seconds, but those have not been observed. So what I focus on is that, so the spin period is like, 70 seconds, like, it's about a minute. This is, it's spinning about itself. In addition, I would couple this with the fact that recent observations indicate that intermediate mass black holes, so this was something observed 2 years back, that they can also be very rapidly spinning, so that the dimensionless spin parameter is close to 1. It's close to like extremely spinning. And it turns out that there is very interesting physics when rotating stars meet Kerr black holes, which is completely unexplored till you. And here I have shown, for example, the angular momentum of the core of the star Okay, when basically it is near the rotating black hole, and here the black hole rotation is taken to be near extremal, and this lambda actually means the fraction of the critical spin. See, because what happens is when if you take a fluid body, if you spin it very fast, because of the centrifugal force, it will at some point just disrupt itself. So we are taking some fraction of that critical spin. That fraction we have taken to be small, that is 0.15. And you see that this can be retrograde, this can be prograde, and this spin 0 means that the star is not initially rotating. So this is what I was telling you, that if you look at the angular momentum of the surviving core, even if it is retrograde or prograde or not rotating at all, the tidal torque will actually spin it up to a very large extent, after which the spin starts decaying, and it's, after some time, it's almost like there is no difference between the. And now, because of the spin, what happens is that, remember that this is very basic physics over here, that I defined the tidal radius as the radius of the star into m black hole by m star to the power 1/3. Now, when something is rapidly rotating and when it has actually bulged, okay, what do you mean by the radius? Actually, I mean, because it's like an oblate spheroid. So you can calculate a volume equivalent radius by thinking that this total volume is effectively the radius of some sphere with some, some radius. And it turns out that that volume effective radius always happens to be more than the radius of the corresponding non-spinning star. So therefore, if the volume equivalent radius is more, the RT increases, so beta increases, which means it has a deeper encounter, which means it would be tidally more disrupted. Okay, so this is one of the basic things that happens. And so therefore, we again went back to our simulations, and this is basically the Kerr black hole, whose metric I have written over here. And so this is the equation of motion for the fluid in GR. And so this u mu is the 4 velocity, tau is the proper time, and so if you actually, this is for a perfect fluid, by the way, and these gammas are the Christoffel connections. So if you set p equal to 0, then of course you get back your usual geodesic equations over here, because this du nu d tau plus this one gamma nu blah blah blah, this is equal to 0. This term over here is basically the contribution of the fluid pressure. And as I said, that the approximation that we are taking is, we are in some sense, we are saying that we will treat this pressure to be in the Newtonian limit, so that I can actually write the so that this part, this is basically the the same equation when I write this down in terms of Cartesian coordinates over here, not Cartesian, I'm sorry, when I write this down in terms of the space-time coordinates. And what we will do is we will sort of treat the first term in a Newtonian spirit. This is an approximation which goes on. And you can see that immediately when you have a Kerr black hole, you have a lot of interesting features, like you could see this is a Schwarzschild black hole, which is the usual precession of the perihelion. And now for the Kerr black hole, the frame dragging effect, you see it has made it almost twice as fast. So therefore, the Kerr black hole is actually a much more interesting thing to look at. And we do this in the presence of a rotating star. And here you go, you see that the fallback rates. See what I showed you a couple of slides back. This is basically the fallback rate for a parabolic orbit. Sorry, for a parabolic orbit for from an intermediate mass black hole of 10 to the power 3. This is the fallback rate from a elliptical orbit of a similar. Well, we have actually taken 10 to the power 4 black hole. So this is the fallback rate for the, and you see how different these are. So therefore, if there is any observational, consequences, they should be borne out by these huge differences in the nature of these quantities, which are actually observed by your telescope. And then, there are some other results. We would not bother too much about this. I'm almost going out of time. And so what we saw was that how the Kerr black hole spin that couples, meaning how the two, the black hole spin and the stellar spin what are the joint effects? And the joint effects, actually, unfortunately, there is not so much in the fallback rate, because what you find is that if you look at the left diagram, for A star is the dimensionless spin parameter, 0.98, almost extremal, and almost extremal in the other sense. I mean, there are not much you could differentiate, but actually, there are many much more differences when you actually talk about the amount of mass left in the core normalized to the amount of mass of the white dwarf, and this is what I've shown. And so basically, here I have plotted something called V kick. That's the last last thing I will introduce. So what people have shown is that because of angular momentum conservation and things like that, when the star disrupts asymmetrically, the remaining core gets a large impulse. And because of that impulse, what can happen is that it can actually, escape from the attraction of the, from the black hole. So these are called hypervelocity stars. And in fact, there are some 8 or 9 hypervelocity stars have been observed. So this is another very important observational signature of tidal effects, that these are hypervelocity stars which you don't know where they came from. So the explanation is that during the process of this tidal disruption, because of asymmetricity in the debris tail, so that star gets a kick. It's called V kick. Okay, and what we found is that this V kick can be very, very significant. And here we have taken a 0.3 solar mass white dwarf, a stellar spin period of 5 minutes, and a 10 to the power 4 solar mass black hole. And the periapsis distance we have taken to be 39 Schwarzschild radii, which is a good enough, distance where you could sort of safely say that your Newtonian approximation to the fluid mechanics will hold. Okay, so I think I have more or less come to the end. So as I said, that there is significant amount of data which is going to come in the next 5-6 years. And so basically the GR aspects, I mean, so in this whole talk, I hope I've been able to impress you that, what we are really looking at are GR, the effects of GR. And you might say that, effects of GR, at this distance, well, there are a lot, as I showed you. I hope I've been able to convince you of that. For example, frame dragging in the curved space-time should produce observable effects. Okay, so, and the effect that I focused on today is the tidal disruption effect. And this is a one graph which I've taken from this paper by Gazeri. This is a review article. But you can see that these are some, I mean, this BB stands for black body. I mean, I don't know, some approximations that the astronomers do. And they are actually plotted these things. You see that this T to the power minus 5/3 roughly is coming out. But there are some of them which don't follow this. So what are the explanations for this? One doesn't know. It's, this is a very recent paper, just about 3 years back. So therefore, my excitement, this thing is that, I mean, how do I test GR at astrophysical scales? I believe that one way to do it would be to understand tidal phenomena, which are poorly understood till now. And for example, there are many other things. Like, for example, you might have heard that when there is a elliptical orbit, when let's say there is in a central force problem, when you have a body and there's an elliptical orbit, if you take the revolving body to be a fluid type of thing, because of energy dissipation, it slowly circularizes. That is, the orbit settles down to a circular this thing. That's why you find that mostly planets and in the solar system, they are close to circular orbits. Okay, and so how does this phenomenon happen when you have frame dragging? Okay, so that's one important question that we are looking at. Like, and there are things like resonance locking for near extremal curved black holes, how these happen, and what type of signatures they can produce is something that we are interested in. The second thing is how disruptions happen near wormhole throats where the energy conditions are violated. I mean, so you don't have a singularity, but you effectively have a throat type of thing. So could you actually, look at some this tidal disruption effects? And because there is a lot of literature on, gravitational lensing and shadows for wormholes. And as people say that, there might be, these may be very similar to black holes and things like that. So is there a way to distinguish them from real dynamics? That's one thing. And the very important thing is that when a star is disrupted very close to the event horizon, particularly important for white dwarfs because, you have the degeneracy pressure where the quantum mechanical forces are into play. And so how do you look at such events? How do you this thing? So one important thing that has happened in the last few years is basically the smooth particle hydrodynamics program that I told you about. People have developed a general relativistic version of that, so that some of these issues about, so when you're going very close to the horizon, you really cannot do the Newtonian approximation to the fluid dynamics. So people have actually come up with some nice things about the general relativistic smooth particle hydrodynamics. But this is in a very nascent stage, a very, very recent development, maybe over the last 1 or 2 years. So hopefully some of these things will shed light in the future. Thank you. I'm done.
Let us all thank Professor Tapobrata Sarkar. So we can take some questions now. Any questions? You may use your microphone and speak. Yeah.
Yes, I have a small question.
Yes.
Yes. So if we want to do some of the simulation on our own, so